intervals are going to be our thing. So we're going to start today by talking about the basics. We're going to get what confidence intervals look like, what are some properties of them, what are their main goals. Okay, and then we'll expand a little bit upon that tomorrow. And then we'll start talking about specifically when we're dealing with proportions. What do our confidence intervals look like? How do we calculate? How do we interpret things like that? When we deal specifically with means, what are those going to look like, and so on. Okay? So we're going to talk in generics today, and then we'll kind of get more specific as we go. So the first thing, in order to work with confidence intervals, we have to have a couple vocab terms here. If we had to give a single number to estimate an unknown parameter, so we want to know the mean height of all students here at PLHX. That might be our goal. We might not be able to, or we might not have the time to go around and find every single student and measure their height. So we want to be able to estimate the average height. Well, in order to do that, what would we need to do? Just a random guess? And where would that educated guess come from?
That's what I've seen.
What? A random sample. Okay? We're going to take a random sample, and we're going to calculate that sample average. That sample average should give us a pretty good estimate for the population average, right? That was the whole idea of the last chapter. If we take a sample value from an unbiased estimator, it should be pretty close to what we're actually looking for, okay? So when we talk about a single number used to estimate a parameter, for means, we use a sample mean. We collect a sample and calculate its average. For proportions, we use a sample proportion. So we gather a sample, calculate the proportion, and use that as our estimate. Okay? Now, this sample mean and this sample proportion have a specific name when we're applying them as estimates for a parameter. And that's a point estimator. That is a term you need to know. So a point estimator is a statistic. It's a value that comes from a sample. And it provides an estimate of your population parameter. Now, the second vocab term up there is point estimate. The point estimate is simply the value that your point estimator takes on. So if we were looking at a problem like I was just discussing, we want the average height of all students at PLHX. So our goal is to find mu, our population mean. So if I took every single student's height and found the average, that would be mu. Now, in order to estimate mu, our point estimator would be x bar. It would be a sample mean. So I would go out and collect a random sample of students and use their average height as an estimate. If I was talking about the proportion of students who like rock music, so either they like it or they don't. So if I went out, I wouldn't be able to ask every single student, so I'm going to take a sample, and I'm going to calculate a proportion based on that. So my point estimator is p hat. It's a sample proportion. Now, when I physically collect my sample and calculate, then it becomes a point estimate. So if they ask, what's the point estimator in this scenario, you're just saying, well, are we using a sample mean or are we using a sample proportion? Do I know which type of problem I'm working with? When it asks for the point estimate, it's saying, what's the actual value? So if I went out and I collected a sample of 50 students and their average height was 5'6", my point estimate would be the 5'6", because that's the actual value my sample mean had. Does that make sense? Okay, so point estimator is what are you using, sample mean or sample proportion. Point estimate is what's the actual value that it took on. So a couple quick examples here. In the following settings, determine the point estimator you would use, and then calculate the actual value. Okay? So if we look at this first example, the makers of a new golf ball want to estimate the mean distance the new balls will travel when hit by a mechanical driver. They select a random sample of 10 balls, measure the distance each ball travels, and then they give the distances below there. So for this particular scenario, what would our point estimator be? It would be a sample mean. Okay? When we look at the words, we're looking at actual measurements in yards. They give us units of measure, which means we're talking quantitative. So we're looking at a mean distance. So our point estimator would be the sample mean. If I wanted the point estimate, so if I wanted to know what x bar actually equals, what would I need to do? Yeah, add all these numbers up and divide by 10 to get the actual average distance. So your point estimator would be x bar. Your point estimate would be the value of x bar, which can be calculated using the numbers there. Okay? Second scenario, the math department wants to know what proportion of its students own a graphing calculator. So they take a random sample of 100 students and find that 28 own a graphing calculator. So in this particular scenario, what would our point estimator be? P hat. So we'd be looking for a sample proportion. What would be the point estimate? 28 out of 100. When you write your point estimates for proportions, so when you write your p hats, you can write them in fraction form. So you could write them as 28 over 100, or you can also write them in decimal form. Okay? So either way works as far as what we're going to be calculating and working with from there. So you can use the fraction form or the decimal. Most often, I prefer the decimal. It's a little bit easier to work with as far as the calculations we'll eventually be doing, but you can choose which way you want to represent it. Okay? So point estimator's p hat, point estimate is the 0.28. Okay with that? All right. So that takes care of our vocab. Now, confidence intervals. So this idea that we're going to be using for the rest of the chapter here. When we take a sample statistic, so when I go out and collect my 50 students and I measure their average height, how likely is it that their average height is exactly the average height of all students here? That would not be very likely, right? So it would be very unlikely that I happen to pick 50 students that perfectly estimate the actual value. Okay? What we know is every time we gather a random sample, we get a new value. Every random sample has different people involved, which means we get different responses, so we get different values. Okay? So we know that our sample statistic is most likely not actually equal to the value, but we know it should be close. Okay? How close depends on how the statistic varies, so it matters how much it varies overall, what's the standard deviation, and so on. And if we take many SRSs of size n from the population. So our sample size can also sometimes affect how accurate we are. Okay? Obviously, the more or the larger the sample size, the more closely we're going to estimate the actual value. Okay? Now, we know from last chapter whether we're working with proportions or means. When our conditions were met, specifically when our large enough conditions were met, we were able to use normal distributions to approximate our distributions. So, when we look at means, okay, we know that the center of our sampling distribution should occur at the actual population mean. So the center of our distribution should match up pretty much exactly with our actual value. But when I go out and collect my own sample, my one sample that I collect, more likely than not, is going to fall somewhere around the mean. It's not going to fall directly on that value. Okay? So this is just an example that shows with different SRSs of 16, the different values you might come up with. Some might be above, some might be below the mean, but we're more likely than not going to get exactly what we want. Okay? So when we're looking at sampling distributions, that's kind of where we're going from. We know that the mean of our sampling distribution should be equal to the population mean, but our actual samples we collect will not give us the exact value. Okay? And with last chapter, one of the big things we knew was we knew the population mean. We knew the population proportion. They gave it to us in the problem. Now think about that. In the real world, if I'm forced to take a sample to estimate my population mean, or I'm forced to take a sample to estimate my population proportion, is it likely that I know the actual value of my population mean or my population proportion? No. And more likely than not, no one knows what it actually is. Right? So one of the things that happens here in the real world, we almost never know our actual population mean. So while we know that the sampling distribution falls the center at the mean of our distribution or at the mean of our population, we don't know what that value is. Because there's no way to actually physically collect the data we need to calculate that particular value. And that's where confidence intervals are going to come into play here. We're going to use the one sample we took to reach out in each direction and hopefully capture the true value. We're going to capture the true mean, or we're going to capture the true proportion from our population. Because we're not going to know what it is, but we want to be able to have an idea of where it should be. Okay? So, in order to do that, we need to go back to an idea way back in chapter 2. The 68, 95, 99, 7 rule. This is something I would probably write down because I know most of you didn't quite understand it fully the first time around. We have not seen it since chapter 2, which means some of you probably need to refresh on what we're dealing with here. So what the 68, 95, 99, 7 rule says, and this is talking specifically about proportions, it can also apply to means. Okay? So, we know that our sampling distributions for proportions and means should be approximately normal. And when we have normal distributions, we have the 68, 95, 99, 7 rule. So that states that 68% of all samples we collect should give us a sample proportion that's within 1 standard deviation of the true population proportion. So if I went out and actually collected every single possible sample of a certain size, and I looked at all of the sample proportions that I calculated, 68% of them would be within 1 standard deviation of that mean. So 68% would be within 1 standard deviation of the true proportion. 95% of all samples will give us a proportion or a sample proportion within 2 standard deviations. So again, if I took every single possible sample of a certain size, 95% of those samples are going to give me a value that became within 2 standard deviations of the true proportion. And then 99.7% of all samples will fall within 3 standard deviations. So in a picture, okay, we know that our mean is located at our population or proportion, right, at P. Now, if I were to reach 1 standard deviation above and 1 standard deviation below, So if I went 1 standard deviation above here and 1 standard deviation below. If I were to imagine taking every possible sample, I should find 68% of my p-hats in this interval. 68% of my value. So each time I collect a new sample, I get a new p-hat. So I might have a p-hat that falls here. The next time I sample, I get a p-hat that falls here. Then I might get a p-hat that falls here, and so on. And I just keep collecting over and over and over again. And I keep collecting sample proportions. What we're saying is that over time, 68% of these sample proportions I collect are going to be within this range of values, from 1 standard deviation below to 1 standard deviation above the true value. If I were to extend out to 2 standard deviations, 95% of my sample proportions should be within that interval. Okay? So again, we're using the idea that with a normal distribution, these three percentages hold true. 68% of all observations fall within 1 standard deviation, 95 within 2, 99.7 within 3. Okay? The problem, we don't know the true proportion. We don't know what our population mean is. We don't know what our population proportion is, which means we can't create an interval based on it because we don't know where to start. In order to create an interval using the true proportion, we have to know it to start with. So we need to reverse things and think of this in terms of p-hat. We know what p-hat is. That's something that we actually physically collect from our sample. So if we reverse this idea and think, okay, well, from p-hat's idea or point of view, what does this look like? So let's think about the 95% level. At 95%, we said we should be 2 standard deviations, or within 2 standard deviations of the true value. Okay? Now, if we're at the 95% level, there's a 95% chance that the true proportion is no more than 2 standard deviations away from p-hat. So if I were to start at p-hat, I know what my sample proportion was. If I were to start there and I reach out 2 standard deviations on each side, somewhere within that reach, so wherever I reach from the left and the right there, somewhere within here, we are going to find the true proportion. We don't necessarily know exactly what it is, but we know there's a 95% chance that I've captured it by reaching 2 standard deviations above and below where I'm currently at. Okay? In other words, reaching 2 standard deviations in either direction, we can be 95% confident that the interval contains the true proportion. So on the last slide, we knew the population proportion, so we knew if we went 1 standard deviation above and below, we were at 68% of all observations falling within there, and so on. But this time, we don't know what the true value is. The only thing we do know is where we happen to fall. We know what our sample proportion is. So if I were to reach out a certain number of standard deviations in each direction, I can have a certain level of confidence that my interval will capture the true value. And that's the purpose of a confidence interval. It's to state that in our sample, this was the actual value we calculated. We found this sample proportion, or we found this sample mean. Now, if we take that sample value and we reach this far in each direction, we can be this % confident that we've captured the true value. And while we might not ever know what it actually is, we can at least zero in on where it kind of is located, what it should be around. Okay? So that's the big idea with our confidence intervals here. So, by taking our proportion and reaching 2 standard deviations above and below, we've created what we would call a 95% confidence interval. If we reached one standard deviation above and below, we would be creating a 68% confidence interval, and so on. Now, one of the things we'll discuss a little bit later on, and we'll get more in depth on, we're not, 68, 95, and 99.7 don't always give us the most options. So we're going to talk about how to use different percentages, like 90%, 99 just by itself, 80%, things like that. So we're going to talk about how to create different size intervals, but the main thing here is understanding what we're trying to accomplish here. Can everyone visualize essentially what we're doing with the confidence interval? We're picking a point to start, and then we reach in each direction a certain amount to try to capture the true value. Okay? So it looks something like this. I'm starting at my sample proportion or my sample mean. So if I want 95% confidence, I'm going to reach 2 standard deviations above my sample proportion. So I'm going to take my sample proportion plus 2 times my standard deviation. And I'm going to reach 2 standard deviations below. So take my sample proportion minus 2 times my standard deviation. That's going to give me an interval. I'm going to be going from this proportion to this proportion. It might be like 0.2 to 0.4. So what it tells me is I'm 95% confident that my true proportion is between 20% and 40%. Okay? So when we're creating these intervals, we're not actually able to calculate where the value truly is. We're only able to say that it should be somewhere within our range of values here. We're trying to center in on the overall. Okay? So, when you look at a confidence interval, some important aspects are how it's created, and we're going to go a lot more in depth into this over the next couple of days. But a confidence interval, what it does, I would maybe write this part down. A confidence interval gives an interval of plausible values for a parameter. So it gives us a set of values we would take to mean are plausible. These are possible values that our sample could, our population value could take on. Now, the way we calculate an interval, and again, we're going to go a lot more in depth on this later on here, but we take our point estimate. So that means we take the actual sample proportion, or we take the sample mean, and we add or subtract what we call a margin of error. That margin of error is essentially the number of standard deviations we want to move left and right. How far do we want to reach in each direction? Okay? So, for instance, in the example here, for a sampling distribution with a mean of 240.79 and a standard deviation of 5. So they took a sampling distribution. This was the mean. This was the standard deviation. If we wanted to do a 95% confidence interval, we take the point estimate, the mean, 240.79, plus or minus, 95% said 2 standard deviations, so we take 2 times our standard deviation. So if we take 240.79 plus 10 and 240.79 minus 10, here's the interval we create. So one of the things to kind of discuss here, if you're given a confidence interval and they ask for the point estimate, So let's say I gave you a confidence interval. You don't need to know anything about it. Let's say I give you a confidence interval of 0.2 to 0.4. So the true proportion should be somewhere between 20% and 40%. Now, if they're looking at the interval and nothing else, and they say, what was the point estimate, how would I calculate that? How would I figure out where the value was they started at? So think about how we created our interval here. We took a point estimate, added a certain number, and subtracted a certain number. In the actual example here, we took 240.79 and we added 10, and then we subtracted 10. So if I was looking at these two values, where does my point estimate, 240.79, fall? Directly in the middle. When we create our interval, we are starting. Point 0 is our sample value. And from that point, we're reaching the same distance above and below. So if they give you a confidence interval and they say, what was the point estimate, they're asking, what point did they start at? Which means they're asking, what's the exact middle of the interval? So if I gave you an interval of 20% to 40%, what's the exact middle? 30%. So my point estimate, P hat, would be 30. Now, if it asked for the margin of error, so 30% is where we started at, what was our margin of error that we used for this particular problem? 0.1. If we look at it, I started at 30%. Well, to get from 30 to 40, I would have had to add 0.1. And to get from 30 to 20, I would have had to subtract 0.1. So if you have the interval, you can calculate the point estimate by simply finding the exact middle, average the two values. The margin of error then is simply the difference between one side and the point estimate.
In the example, why was it 10? Like, why did they add 10? Why did they get 10?
So the 10 there came from, when you calculate the margin of error, this is something we're going to talk a lot more about later, but we had the standard deviation of 5. So if I want 95% confidence, remember that meant I want to reach 2 standard deviations above and 2 below. So I'm going to reach 5 units twice above and twice down. Okay? All right, so that's the idea of calculating a confidence interval. And like I said, we're going to get a lot more in depth with that. We're going to get a lot better with that as we progress. Okay? Here's a cartoon example. This kind of leads us into some of the later discussions. Okay? So notice in the example there, he gave a confidence interval. He said the temperature will be between 40 below zero and 200 above, right? Is it likely that he's going to be wrong? No. Okay? When we think about it, as far as temperatures go, do we ever really see anything below 40 or especially above 200? No. So technically, he knows where the temperature is going to be. It's going to be between those two values. Now, do those two values really give us anything to go off of, though? Would an interval of that nature really be useful to us? No, because it doesn't zero in on anything. So one of the things we're going to talk about over and over and over again when we go through these confidence intervals, we always want to try to balance how confident we are that we found the true value with the width of our interval. How wide do we want to reach? Because the wider we reach, the less accurate we can be in predicting the value. But the more we want to zero in, the less confident we can be that we've captured the value. So it's going to be a balance between how accurate we want to be and how confident we want to be. Now, one of the most important things from today is right here, interpreting your confidence interval. So when they give you a confidence interval, being able to interpret it is extremely important. So this essentially gives you your blanket statement. Anytime they ask you to interpret a confidence interval, you can make this statement. All you have to do is insert context. So if you're working with a 95% confidence interval, you would say we are 95% confident that the interval from whatever the low value was to whatever the high value was captures the actual value of the proportion of whatever, or captures the mean of whatever. So what was the actual parameter of interest? So when you're asked to interpret a confidence interval, this is kind of the blanket statement you use to interpret it. So whatever confidence level they had, you report that. So 90%. We are 90% confident that the interval from 0.2 to 0.4 captures the actual proportion of whatever. We are 99% confident that the interval from 2.7 meters to 5.6 meters captures the true mean of whatever. So it's what confidence level you are using. You're going from low value to high value, and you're capturing the true proportion, or the true mean of whatever. That's where the context comes in. So that ending point is where it's going to change the most, is what context are you working with. Okay? So an example. 2 weeks before a presidential election, a polling organization asked a random sample of registered voters the following question. If the election were held today, would you vote for candidate A or B? Based on this poll, the 95% confidence interval for the population proportion who favor candidate A is 0.48 to 0.54. So they gave us a 95% confidence interval. They said the proportion, the true proportion should be between 0.48 and 0.54. So if we want to interpret this, what statement would we make? We are captures the actual value of the there we go. That's where the context comes in, guys. So we were talking about proportions, which means my parameter is a proportion of something. Okay? So when we go to fill this in, the confidence level and the blanks are very easy, because they're going to tell you the confidence level and they're going to give you the low and high value. So we're 95% confident that the interval from 0.48 to 0.54 captures the actual value of the proportion who favor candidate A. Okay? So we're going to capture the true proportion of people who favor candidate A. If it was a mean problem, we would say we're 95% confident that the interval from, let's say, 0.48 to 0.54 captures the actual value of the true mean of whatever was in the problem. Okay? So that's the big thing when you're working on interpreting the confidence interval. The first part is usually pretty straightforward, so they're going to give you all that. The thing you have to look for and be able to put into words is the context. Okay? All right? So based on the confidence interval, what is the point estimate that was used to create the interval? So if we want the point estimate, we need to know the point estimator, which in this case is p hat, right? We're talking proportions. So what's the actual value of my point estimator here? 0.51. And we got that because? Yeah, if we average the two, take 0.54 plus 0.48, divide by 2, that gives us our exact middle. Point estimate is always the exact middle of the interval. So 0.51. Now, what's the margin of error? 0.03. And we get that because 0.51 plus 0.03 gives us 0.54, and 0.51 minus 0.03 gives us 0.48. Okay? So point estimate is always the exact middle of the interval. The margin of error then is the difference from that point estimate to one side or the other. You okay with that? Okay. So then based on this poll, a political reporter claims that the majority of registered voters favor candidate A. Use the confidence interval to evaluate this claim. So the reporter is claiming that the majority of voters favor candidate A. So think about what that means. If I'm looking at a majority of voters, we're talking proportions, right? What would that mean in terms of proportions? Well, 0.5 would be the cutoff, so a majority would be 0.5 or more, right? So more than 50% of the voters support candidate A. Now think about what our confidence interval tells us. Our confidence interval says that the true proportion of people who favor candidate A should be between 48% and 54%. Do we know exactly where it falls in that interval? No, we don't. So this reporter is claiming that more than 50% of people, guaranteed, more than 50% of people support candidate A. Can we make that claim based on this interval? No, why not? Because less than 50 is in our interval. We could have someone just over 48%, or we could have 49%, or we could have 48.6%, right? So the fact that there are plausible values less than 50% means we can't say for certain that more than 50% of people support candidate A. Okay? Now, what if this reporter had claimed that more than 45% of people support candidate A? Now we can logically make that assumption because our interval is entirely above the 45% cutoff. So since it's all the way above, we know that in most cases, we can be pretty certain that we have more than 45% approval. Okay? So when you're looking at interpreting based on the interval, you got to think about where the value they're questioning lies and how it relates to the interval itself. Okay? All right, last thing here. When we talk about 95% confidence, or we talk about 90% confidence, we talk about 99% confidence, what does that confidence mean? Okay? So each confidence interval uses a statistic to estimate a population parameter. Now, since every sample we collect will vary, that means every sample we collect will create an entirely different confidence interval. If I had each of you go out and collect a sample of students, and you all calculated their average height, and you calculated a confidence interval for that average height, you would all have a different confidence interval because each of you had a different starting point. Okay? So, when we say we're 95% confident, what that means is if we were to create every possible confidence interval, so if we collected every possible sample of a certain size and we calculated the confidence interval associated with that, 95% of the intervals we create will capture the true proportion. So in this graphic here, this green line represents the true proportion, or the true mean. These blue lines are denoting the confidence intervals. So the red dots are the point estimates, and then we're reaching above and below from there. So notice the very first sample we collected created an interval that did not capture the true value. The next one did because the green line passes through the interval, and then the next one did, and so on. And then we get to the sixth one, it doesn't capture, and we continue on. So what we say when we talk about confidence level, it's telling us that if we were to take every confidence interval possible, that percent of the intervals we create will capture the true value. Does that make sense? So what they're telling us is it's not a guarantee that when we create these intervals that we do in fact capture the true value. That confidence level tells us how confident we can be that we actually have. So when you interpret confidence level, 95% confident means if we take many samples of a certain size from our given population, about 95% of them will give us an interval that captures the true value. Now, one thing people tend to misinterpret here, this does not mean that when I create an interval, I have a 95% chance of capturing the true value. So it doesn't give us the probability that one single interval in particular captures or doesn't capture the interval, or the true value, which should make sense. If I create an interval, so I have an interval set up, what are the only possible probabilities on whether I capture the true value or not? If I've created my interval, what are the only two probabilities that would make sense for whether I captured the actual value or not? So either my interval captured it, which would be a 100% chance I captured it, okay? Or my interval did not capture it, which is a 0% chance that I captured it. So each individual interval doesn't have a specific probability of capturing or not. It's either going to capture or it's not. What we're talking about with the confidence level is, if we were to do this over and over and over again, our intervals should eventually come out to be 95% capture, 5% not. Or if I had a 90% confidence level, 90% should capture, 10% should not. Okay? So, here's your assignment. So go ahead and get this written down real quick, or take a picture with your phone. The blogs are still down. They don't have any idea when they're going to be back up. As soon as they are, I'll continue to update that.
Mackenzie Cartwright, please go to the health office. Mackenzie Cartwright. Jade Pierce, please come to the attendance office. Jade Pierce. Thank you. Thank you.